In this video, we'll be talking about some of the steps we can take to actually reduce noise. I've got a practical example at the end where we're inducing noise onto the line so you can actually see some of it. But think about some of the ways we can actually reduce this. Well, one of them is our proximity from the wires or sensors that we're using, or wires that are carrying our communications, to whatever's generating that noise in the first place. For example, we might move our signal and communications wires further away from our power, or maybe we've got some wires driving a motor or something like that. And the further we have them away, the less noise will be induced onto those particular lines. And we've got things called ground loops where we can induce noise into our system from other devices as well. Our wiring might be poor. We might not have shields, and the shield is important for reducing the amount of noise that can be inductively coupled into a wire. Or maybe those shields are broken or frayed or damaged in some way, and so we've got noise that can come into our wires because of that. If you look at the picture above, you can see our digital signal and our analog signal. We can more easily recover the data from our digital signal because we're quantizing it. With our analog signal, well, that noise is causing it to go up and down quite a bit. Where our digital signal, we know whether it's essentially going to be a 1 or a 0, most of the time at least. There's different ways we can do digital communication as well. And one of them is in using differential wires in our communications. Lots of systems use this, like Ethernet and USB, for example. And these basically give us double the voltage separation between ones and zeros. They help us reject noise, common mode noise, and help us reduce the amount of noise within our system. So that's a useful way of transmitting data and reducing noise in it. If we've got lots of long leads, those long leads act a bit like antennas. And you know from when you've used antennas in the past, if you extend the antenna up, you'll pick up more radio stations. You'll pick up more noise as well. And so we've got more noise being induced into our system. Now, when we're using things like relays and motors, we need to do a bit of signal conditioning around them as well. So having a flyback diode across relays will stop a whole lot of noise being induced into the system when the magnetic field collapses, and you can get voltage transient spikes into the system. Likewise, putting some capacitors across DC motors when they're starting and stopping can shunt the noise through the capacitor and reduce the noise that's being brought into the rest of the system as a result. Another way we can reduce noise is filtering. And basically what we can do is we can choose a frequency or a set of frequencies that we want to reduce. There's different ways we can do it. We can use what we call analog filtering, where we have a bunch of different components, resistors and capacitors and inductors, for example. And those components we can put in various configurations. We're not going to concentrate on this class to reduce our noise. The other thing we can do is digital filtering, where in software we can create a number of different filters as part of our digital signal processing, or DSP, to reduce our noise. Now, the four basic types of filters are our low-pass filters, which allow low-frequency signals to pass but attenuate or chop off or reduce those high-frequency noises. Likewise, the opposite of that is a high-pass filter. We've also got band-pass filters, where we've got a certain frequency we want to let through and we filter out other frequencies. And finally, a notch filter, or band reject filter, where there's a certain frequency band. For example, with that 60 hertz or 50 hertz that we get from power lines, we want to reduce everything from maybe 49 hertz to 51 hertz. So we can reduce that in there. Now we'll look at some practical examples of noise being induced into a system. I'll now give you a few practical examples of measuring noise in a system and demonstrating how that noise can be coupled into a system. So over here we have a digital oscilloscope. A digital oscilloscope is basically a fancy piece of equipment that allows us to measure voltage as it changes over time. And so if we put in a sine wave that changes over time and goes up and down, we'd see that sort of thing. We have the probe that's connected to that. That's what we connect to our electrical equipment. Now, we're not going to connect this probe to anything, and we're going to show how we can induce noise into this probe. First off, I've got a cable here. And this cable is just a power extension cable plugged into our power point. But let's see what happens when we bring the probe of this right up close to our signal. We'll have to adjust our scale, and we should see we're getting a little bit of noise from being coupled in And if I change our frequency a bit, we should see, there we go, that noise we're getting in there is at 50 Hertz. Now this power cable, AC current, 50 Hertz that we're getting there. Now let's look at a few other things that we can do, because that signal there is really pretty small. That's because these cables here are well shielded, but let's just connect a cable here, and this is just a short length of cable, and oh, look, the signal here we're getting is a lot larger. Peak to peak, it's about 100 or 200 millivolts from peak to peak. Now, if I touch it with my finger, so this piece of cable here is acting like an antenna. If I touch it with my finger and take this off, my body's acting a bit like an antenna as well and picking up electrical noise from the air. So we've got a whole lot being coupled in here. Now, I mentioned previously that we've got switching that can occur from electric motors. So here's an electric motor. I can press a switch here and turn it on and off. Let's move this cable a bit further away. So that's not interfering quite as much as what it was, but it is still interfering and coupling noise into our system. But if I turn on and off my electric motor, you'll see that there's all these little peaks that are occurring now in our digital signal that aren't there when we had nothing there. So what we'd be expecting, what we'd be hoping for in a nice clean system is this is just a flat line because there's no signal in there. The only signal that we're getting at the moment is a noise-based signal. So there's our signal again. Let's put this cable around here a few times so we can couple in the noise even better. And let's see if we can... Oh, we're getting heaps of noise off that electric motor. So there we go, a few practical examples of showing how, particularly when we've got a long cable that's acting a bit like an antenna, we can couple all sorts of noise into our system. When we take it off, you'll notice we've got very little noise there until, if we put this very close to, and if we turn it right down, if we put it very close, we're starting to get a little bit of noise coupled in. But you'll notice as soon as we move it further and further away, very little noise coupled in. And so distance is playing a significant part in how much noise is being coupled in. Distance as well as shielding.